Yeah, so we're going to be looking at a
Excuse
few
me, sir.
applications. Yeah,
About test one, when will you give it back?
you were somebody who missed it.
Yes, I did message you and you said okay.
We're going to talk about that at the end, right?
Okay, sure.
Yeah, good. So we're going to cover some basic applications of integration, right? Let's start with maybe kinematics, right? This is an M, matics, right? I think when we did differentiation, we did say that if you have um, the displacement as a function of maybe time, when you differentiate, you will get velocity. And if you were to differentiate velocity, you will get acceleration. You can guess what we can do here. If you have acceleration and you integrate, you're going to get velocity. And if you were to integrate velocity, you will get displacement, right? And this is the application we're going to be concentrating on, doing the opposite, right? Right. Remember, integration is the opposite of differentiation, right? So, so for example, just illustrating, if you have, we know that v is equals to ds dt. We know that, right? So if you were to separate the variables, right, you get what? Um, you'll get the integral of let me write it like this. I hope you can get to how I got this, right? V dt, right? So if I take this across there, right? Well, I'm writing the ds in front here. So this is basically saying that, okay, if you integrate 1 with respect to s, you're going to get s, right? So s then is equals to the integral of v dt, right? And that's what I'm saying here. If you integrate v, you're going to get s. That's what this is saying, right? Similarly, we know that acceleration is equals to dv dt, right? The derivative of the velocity gives you the acceleration. So again, you separate the variable. This process here is called separating the variables, right? So a dt equal dv. I'm gonna put this in front, right? So the integral of dv is equals to the integral of a dt, right? So if it's like a 1 in front here, 1, you integrate with respect to v, you get v equal to the integral of a dt, right? You integrate acceleration, that's what I'm saying. You integrate acceleration, you're going to get velocity, right? Simple as that. Nothing difficult for you to just remember that. When you integrate acceleration, you're going to get velocity. When you integrate velocity, you're going to get displacement. That's basically what it is, right? All right. Let's take an example to illustrate that, right? So, all right. Give me a chance to. I was gonna snip this problem from. Okay. All right. Good. So look at this one. Uh, so we have an object. It's falling from a building freely, and the acceleration basically. That's what this is saying, right? This is the acceleration. dv dt is the acceleration. It's what we call acceleration due to gravity, right? It's around 9.8, but I'm just using a nice number, 10 instead of the 9.8, right? They ask you to find equations for the velocity and displacement of the object from the top of the building, right? So we just said that the integral of dv is equals to, or in other words, v, right? V. What am I doing? Yeah, just write v. V is equals to the integral of a, which is this, right? 10 dt, right? So this tells you that v equals to 10t, right? And if you want, stick in your k. Remember your k? Remember your k, right? So your velocity is equals to 10t plus k. Now there's a way you can evaluate this k, because they said here that you're dropping an object from the top of a building. So in other words, v equals 0 when t equals 0, right? So that would make what? If you put 0 equal 10 times 0 plus k, that tells you that k equals 0, right? So your velocity then, the expression for your velocity is really 10t, right? And then we just said from the previous slide, previous part here, that s is equals to the integral of v dt, right? Which is, we got v now. So it's equal to 10t dt, right? The integral of that, which is, what is it? 10 over 2, 5 t squared. And you can again put your k at the end there, right? And we can evaluate our k, right? Because at the top of the building again, when t equals 0, s is equal to 0 as well, right? So we can evaluate k. We can evaluate k. Let's move it up a little. So 0 is equals to 5 times 0 squared plus k, which implies that k equal to 0, right? So your expression for displacement is s is equals to 5t squared. Simple as that. Tell me if you follow.
Yes, sir.
Okay. Taking another one. I'm copying from I'm just borrowing it from a book of down here. Right, let me see. Nope. All right, look at this one. Look at this one. So, oh, this thing, what is this thing doing here? Here. So the velocity of some particle moving in a straight line is given by this expression v, right? V. And they ask you to calculate the initial velocity, the distance gone in the first 5 seconds, the average velocity during the first 5 seconds, the velocity after the, oh my, a lot of things. Sorry, good. Let's not every single thing is going to involve calculus, right? But whatever involves calculus, where we're going to use it. So they want the initial velocity. In other words, they simply want when, this is the A part, right? When t equals 0, v equal 20, right? See if you agree with that. I have to do nothing there. when t is 0 here. Initial velocity means you haven't started to count time yet, right? And time is 0, right? So the b part now. The b part, remember, s is the integral of v, right? S is equals to the integral of 20 plus 4t dt, right? Which will give us what? It will give us what? 20t plus 2t squared, right? Plus again your c, or if you can use k, right? Doesn't matter. And you have to evaluate c, right? Well, they're telling you that, well, all right, when t equals 0, all right, no, we wanna evaluate c. When t equals 0, right? S is also 0, right? Because well, that's our assumption there that, you know, the things start to be starting to count distance from when t is equal to 0. So that implies that c equals 0, 0, right? So the expression for s then is going to be s is equals to 20t plus 2t squared, right? So there's no calculus so much there. But they want the, oh, we aren't done. We want the distance gone in force 5 seconds, right? Oh, so what we could do is substitute. You know what? There was another way to do this simply, and we didn't have to evaluate c. I'm going to show you just now. So the force 5 seconds, in other words, when t equal to 5, right? S is going to be equal to 20 by 5 plus 2 by 5 square, right? All right, just so, yeah. And that will give us, what is it, 100 plus 50, 150, 150 meters. Right, that's 1 V. All right, leave that all the way to for when I tell you about something called the fundamental theorem of calculus. I'll tell you that later on. Yeah. And they say the average velocity during the first 5 seconds, right? So we know the initial velocity is 20. Okay. After 5 seconds, oh no, we're not gonna check the velocity, average velocity like that. Average velocity is what? Total displacement over time, right? Isn't that so? So it's going to be 150 over 5, right? So you get what? 30 meters per second. And then the last part says the velocity after 5 seconds. All right, so here we got an expression for the velocity. Where is it? We got an expression here. So you just have to substitute, right? So V when t equal 5, right? Let me put it like this. Is equals to what? 20 plus 4 times 5, which is what? Do I get it right? V equal 20 plus 40. We got 40 meter per second, right? You don't have to do no calculus there. It's just substitution in the expression for velocity. No calculus at all. You follow the example? I'm not hearing any feedback and so on.
Yeah, sure.
Very simple, right? Very simple. Just remember, to get if you're given acceleration and you have to find velocity, you integrate the expression. If you're given velocity, you have to find displacement, you integrate the expression. The hardest thing is that they need to evaluate the K or the C or the constants of integration. You would have to make use of what they call initial value condition, right? And there's where some reasoning might come in, right? Like look here. Here, when t equals 0, v equals 20. You can see that from here. When you put t equals 0 here, v equals 20. That's an initial value condition, right? Here, when t equals 0, s equals 0. That's an initial value condition. And that helps us to get the value of c. So sometimes a bit of reasoning, like the last problem, when you drop the ball from the cliff top, when t equals 0, v equals 0, now so? Similarly, when t equals 0, there's no distance traveled, so distance is also 0. So those initial value conditions can help you to evaluate your constant of integration. Right? So keep those things in mind, right? All right. So let's go to another application, right, of integration, and this has to do with area, right? It has to do with area. So give me a second. I just want to copy this. No. Okay, this is what I want. But I expanded this thing, the thing is a little fuzzy. So this is basically a core of fx, right? I think what they have here is this supposed to be x equal a, and down here is x equal b, right? Yeah, I think that's what they meant there. And basically what they're telling us here, right, is that they want us to find that area, and this time the area is between that function and the x-axis, right? They want us to find that area there. And so in order to find this, let me just give you a quick bit of how they came up with this whole thing, right? And I don't know if you all did this in high school, where they took this, let's say you take this little this area here, right? And you were to divide it up into little, I think in high school they tell you trapezium, right? And what sometimes you can think of this as little rectangles, little rectangles, you know, all these little rectangles, right? So, okay, this one is going to overshoot on top there. This one is going to come down here, you know, and they take the area of all these little rectangles, and they kind of make the width of each rectangle so small that the area of all those little rectangles approximates to the area under this core, right? And what they found out, I'm not going to get into the history and all the how they actually came about with it. They found out that the area under this curve basically is this, right? So, and let me write it. And this is what they refer to as the fundamental theorem of calculus. They're basically saying the integral of fx, right, from a to b dx is equals to fx, right? Where fx is what we call the antiderivative of fx, which is, in other words, the integral of fx. And sometimes you see some of them use one bracket like this, some use two, ba, which is really equal to f of b minus f of a, right? Where f is the antiderivative of fx, right? That capital F is the antiderivative of or the integral, right? And that's where they came up with this thing. This is called the fundamental, where can I write it? The fundamental theorem of calculus, right? What the statement is basically saying is that if you differentiate capital Fx, you get Fx, right? Common Fx. And if you were to integrate common Fx, you will get capital Fx. It's simply saying the integral of this common Fx, or the integral of the derivative, is the function itself, right? Is that easy to get? The integral of the derivative gives you the original function. That's what the fundamental theorem of calculus is saying, right? In other words, integration is the opposite of differentiation, plain and simple. But we're going to use this idea. They found out that the area under here is actually this, right? And we process, and if the graph is oriented the other way, let me just show you what I'm talking about. If the graph is oriented maybe like this here, you get this here, and maybe there's a curve, all right, let's just call a curve like that, and you want to find this area, right? All right, oh, I should say something here before. Down here, oh my, yeah, this here, right? If you let y equal fx, so the area here is equals to the integral of y dx from a to b, right? Because usually y is some expression with x inside, x squared and 2x plus 1 and all of that. Good. If the graph is oriented differently, like this here, you want to find this area, right? So the area, okay, let's say down here is, from here is a to b, right? Area is equal to the integral of x dy from a to b, right? We're going to do an example just now to show that, right? We're going to do an example to illustrate all of that. So, yeah. Let's do an example to bring all of that out. So I'm going to borrow a little, so if you have a curve, and the curve is the curve, let's see, all right, y equal e to the x, right? And you want to find the area between 0 and, let's say, 2, right? So this area here. What's the area here? What's the area here? Right? So it's simply, its area equal the integral of, okay, of y dx from 0 to 2. Y happens to be, in this case, what's that? E to the x dx, right? And you integrate e to the x, you get what? E to the x, simple, right? 2, 0. And how do you fix this now? This now means this. E to the 2 minus e to the 0. Right? You simply substitute 2 in place of x and then 0 in place of x, and you subtract. And you get, well, this, you can leave it like this, right? You can leave it like that. If you want to evaluate it, that's up to you, right? You're just going to get an ugly decimal. you're just going to get an ugly decimal. Easy to follow? I almost don't drop asleep, I know. All right, let me do another one. So you have this curve, and um, I'll write it this way. You have the curve x equal to 4 minus y squared. All right, and you want to find the area between this curve and the y-axis, and the y-axis, not x-axis, right? So the curve looks like this, something like this. Curve is like a quadratic, comes like this, right? And you might want to find out what this is and this is, right? So you put x equals 0 here, or you put x equals 0, right? So to find the intercept, right? You want to intercept. Y-intercept, intercept is when x equals 0, right? So but 0 equals 4 minus y squared. So y turns out to be plus or minus 2, right? So we're going down here is minus 2, down here is 2, right? Good. So we're finding this area here. We simply, remember we said area equal to the integral of x dy from, well, in this case, minus 2 to 2, right? So you can have what now? Integral of 4 minus y squared dy from minus 2 to 2. So evaluate that, we'll get some horrible looking expression now. So when you integrate 4, you'll get 4y. When you integrate y squared, you're gonna get y cubed over 3, 2 to minus 2, right? If you're smart, you can actually take from 0 to 2 and just double the answer. You get the same thing, right? Which turns out to be, you substitute, right? You substitute 4 times 2 minus 2 cube over 3. Right, so you get 4 times minus 2 minus 2 cube over 3. All of this supposed to simplify to 10 and 2/3. Right? You'll do your arithmetic. You with me?
Yes, sir.
Okay. Let's take a final one. Let's say we want to find the area between y equals 4x cubed. Should I put in 4? Why don't I use just x cubed? Let me take out the 4. See a set of mosquitoes come down here, man. Oh, I think I know. All right, let me keep the 4. Let me keep the 4. I don't know why. It will kind of get our, right? Yeah. So we want the area between, all right, let's just get that graph. So the graph will look something like this. Right? Oh, God. Yeah, don't kill me for this. Let's say you want the area between, let's say, minus 2 to 2, right? So it's this area here, all this. Let's see what happens. Let's see what happens. So we put, all right, area equal the integral of 4x cubed dx from -2 to 2, right? So we get what? This will be x to the 4 from 2 to -2, which is equals to 2 to the 4 minus -2 to the 4. And guess what you'll get? Somebody tell me what you'll get. Hmm?
2 to the 4th power would be 16. Negative 2 to the 4th power would be 16. So 16 subtract 16. Yeah.
You get 0, yeah. But this area is not 0. Right? You realize that, right? You get what I'm saying?
Yes, sir.
So what you need to do in this case, and that's why I always say that, the mathematics will churn out an answer, but you have to analyze whether it makes sense, right? You understand? So what you need to do in this case, you need to take these areas in pieces. You take from -2 to 0. I'm not going to do that. I'm going to leave you to do it as an exercise, right? Find the area from, all right, the area from area, all right, call it area 1, call it A1, and call this A2. I call area 1 to be what? The integral of 4x cubed from -2 to 0. Do that. And then find area 2, sorry, which is equals to from 0 to 2, right? 4x cubed dx. Evaluate these two. You might even find, you might find that this one might be a negative answer. But you know that area can't be negative. Area is positive, right? So you will use the positive value and the positive. Well, these two are identical, right? You can even find this and double it. Okay, you know that the two parts of the graph is symmetrical, right? You can do that, right? If you find this to be a negative value, well, you don't use the negative sign because you can't have an area that is negative. Area is always positive. Is that clear?
Yes, sir.
Yeah, keep that in mind. All right. I hope the others are following and so on. You try the thing, try it. Don't play lazy. The online thing making you have very, very lazy. What if you have two curves? Area between two curves. Area between two curves, right? Between, I'm just going to use between curves. What are we talking about? Let's say you have a graph, two graphs, maybe one graph looks like this and the other graph looks like that, let's call this one, all right, fx, and maybe this one is gx, and you want to find this area here, right? So what you want to do probably is find the intersection here. So let's say down here is A, down here is B, right? And like in high school, I don't know if I remember when we were in high school, and I remember teaching this, no doubt you remember it too. Like if you have a circle, right? And you have a sector, and then you have a segment here, and you want to find this area. Anybody can remember what you do? You want to find this area. What do you do? You have a sector, you have a segment, You want to find the area of the segment. Is that the right word I'm using? Anybody with me?
Sure, you find the area of the entire circle and subtract the triangle.
Would that give you the area of the segment? Any other person wants to try? Not remembering that from high school. Oh gosh. Anybody else wants to try? And these are basic problems, you know. Nobody else knows what to do. It's not calculus, right? It's not a calculus course. I'm asking common sense here.
Sir,
Go ahead.
isn't there like a formula to find the sector by itself?
Yes, there is. Yeah. So what are you doing with that? Tell me.
So what if you find the area of the sector and then find the area of the triangle and subtract both?
Brilliant. That is what I'm talking about. Yeah, that's the idea there, right? Yeah, very good. Right? And that is what we're going to apply here. We want this area, right? We want this area. Very good. Matura said that. Yeah. So we're gonna find this whole area. We're gonna find the whole area, so right? We're gonna find the whole area. And then we're gonna find the area, this part here, right? And we're gonna subtract it. And that will give us this area here. Right? That's what we're gonna do. The exact idea. Right? So yes, this might be the thing you do at CXC, but you apply it here, right? Yeah. Good. So basically, the area that we're talking about here, right, is going to be equal to what? It's going to be equal to right? So it's the area under fx, right? The area that's bound by fx and the x-axis, which is this piece, minus the area under gx and the x-axis, right? We subtract it too. It's the same thing. It's the same thing. It's the same thing you're doing. Let's illustrate with an example. See if you follow. Right? I can write it like this. I can write it like this. The integral of fx from a to b, right, dx, minus the integral of gx with respect to x, right? It's the same thing. That's the same thing. You could do it like this. That's not a problem. It's the same thing. Good. Let's do an example. Bring that out, you know. So let's say you want to find the area bounded by, find area bounded by y equal x squared and y equal 2x minus x squared, right? So we got these two curves. So we want to know what's that area that, you know, has been between these two curves, right? And here is where you'd have to know a little bit. This place is getting warm, but let me get some breeze. Yeah. And we'd have to have an idea of these graphs, right? And it goes right back to our algebra course and so on. That's why I'm preventing these students who wrote algebra and failed not to do this course, right? I'm telling them not to. I'm not going to record their scores if they find themselves in this class and do the test and all. I'm not recording their scores, right? I hope they get that message. I probably have to put it back in a group. If you fail algebra, you can't do this course. right? I'm doing you a favor because you can do much better than that. I mean, you might do the course and scrape a D and all of that, right? But it's not good for you, right? It's not good for you. When you get a fail grade, it doesn't goes towards your GPA. You do back the course and you can get an A, right? But if you do this course and you get a D now, it's only pulling your GPA down. People don't understand those. The mathematics beating everybody up, man. Right? It's simple mathematics. They don't understand this GPA thing. Right? So when they're calculating GPA, they don't consider the F. Right? So, and I've seen students who they have an F this year, but they make up their mind and they mature a little bit and whatever. And next year they get A in algebra and say, what? Right? They go proceed now to calculus and they ace it. They got, oh my, another A. So here you have two A's instead of an F. And then, well, you got to do back that. And then you got a D, right? GPA is everything, right? Especially how UG is getting free now, right? UG is free. You can see the Burbis area is flooded with people, flooded with people. If somebody hires you with a low GPA, know that they're going to underpay you, right? They just need somebody to fill a hole, right? As well as sometimes the work has no, no relationship to what you studied. The other day I met a parent and I remember that student very well. And one thing, nobody listens to advice from me. Yeah? And when I found out the girl is working at a place that has nothing to do with biology, she did a whole degree in biology, right? Nothing to do with biology. I said, oh gosh, waste 4 years. And that time they used to pay that is nearly what, 4 year, more than $1 million, right? And there's only tuition. And now you go and get a job that has nothing to do with what you studied. By the time you work 1, 2 years at that place, you forget all your biology and you just like when you came out of CXC. You know, you want to make sure you really do the work, get good grades, get a good GPA, and you want to, get into an area, right, that is relevant to what you studied. And mind you, I was telling some group of students, if you don't get into medicine or you don't become the doctor that you aspire to be, right? That's not the end of the world, right? There's so many careers out there, right, that are fulfilling, right? And it's, I mean, the pay is good, and you can very well do something meaningful. Like the other day, I think the EPA, sorry, I didn't even know that EPA exists in Borbies. I didn't know that, right? The EPA was looking for somebody, not one person. I think they want 2 interns who I think they will eventually employ, right? I think they want them as interns, and after I don't know if it's a year or 6 months. I didn't read the email, but I suggested a name because one of the lecturers gave me a name, and I think the Agri people suggested a name. They wanted somebody who did environmental science too, but because of the biology that they did, and so they have an appreciation of the science, right? And that's a good area. You get into looking at the environment and so, right? Conservation is a big thing, Yeah, so I hope those people are taking note. I'm going to put out a notice to that effect. Yeah, let's go back to this here. So you have to know what the curves look like, right? So basically this curve, let me give you an idea of what it is, right? Because in the test, you have to, x square, all of you should know x square looks like this, right? It should be a little more curved there. And this one here, right? If you were to factorize, let me just give you an idea. You get x into 2 minus x, right? So this is telling you that the curve passed through 0 and 2, right? 2. So the curve looks like this. Oh gosh. Oh my, horrible. Horrible. All right, let me do that back. It's gonna work, man. So you see the curve coincide at 0. What's this number here? What's this number here? Right? You put the 2 equal, right? Put x squared equal to 2x minus x squared, right? And when you factorize that and so, you get x equals 0 or x equal 1. I'm not going to do it for you. So this here is 1. So we want to find this area here, where the two enclosed there, right? So the greater curve is the x squared curve, and the lesser curve is 2x minus x squared, right? So the area then, area is equals to the integral from 0 to 1, right? Because 0 to 1 of, oh, sorry, the greater curve is not the x squared, it's this one, 2x minus x squared. Yeah, 2x minus x squared minus x squared, right? Dx, right? So what's that going to simplify to? 2x minus 2x squared, right? You integrate that, you can pull out the 2 in front, you're going to get 2 the integral of x minus x squared, right? Leave the 2 outside and you get equal to, I mean, I have to move up this whole thing. Pull this 2 in front, you get what? 2 bracket, integrate that, you'll get x squared over 2 minus x cubed over 3, right? From 1 to 0, right? So you put, well, 0 will kill all of this, right? It's basically equal to 2 times 1 over 2 minus 1 over 3. You get 1/3 is the answer, right? No need to substitute 0 in here because everything will be 0. So here I'm just substituting the 1, right? There's no need for substituting 0. And your answer is 1/3. And it does look so, a small space in there, right? A little more work, Can I move away?
Yes, sir. Now you can move.
Okay, good. All right. So we'll move away from that and we'll go to applying it to volume, applying integration to calculating volume, right? And basically, if you were to take let's say let's say you have an object that maybe it's like, all right, it's like that, all right. It goes like that. It goes. I didn't tell him this thing to put this thing straight, All right, but all right. Let me put it like that, right? So this is like a solid something, right? This is like the face, and it's as though if you watch it good, it's as though you take an area, right? You take this area, and you were to revolve it. That's why in the textbooks you'll see that about solids of revolution. They call it that, right? So if you take this area, it's like a disc, and you were to rotate it right away around. And let me not use the word rotate, use the word revolve. Revolve it. The textbook does use the word rotate too. Around the x-axis, this area is going to actually create a solid like this here, right? And you can actually calculate the volume, right? You can actually calculate the volume of that solid that is generated, right? And that volume, actually, you can write it like this. I'm not going to get into how they came up with it and so. The integral of that area in terms of x dx, right? Instead of writing it that way, mathematicians have made it even easier for us. I was telling the engineering class that I have, I was showing them some formulas and so on, and they were amazed. They were pretty amazed, and they wanted to get into how they came up with it and all. And I say, your program of study, you don't have to be interested, or not that you should be interested, but you don't need to worry about how we arrive at the formula. The mathematicians did the work for you. Your work now as an engineer is to use it to make sure that whatever you build, right, whatever you design and build, well, the thing will work, right? It wouldn't fail, right? So, yeah, lots of times people don't appreciate the work the mathematicians do, right? So the volume, and I'm going to give you like this, the volume is going to be equal to pi times f x square dx, right? Sometimes you see it like that. If you revolve this this area around the x-axis, this is your volume. Written another way, you see it like this: pi of y square dx, right? See that? Some fx, they use y. Right? So you take the square, and basically, if you watch it good, right? If you watch it good, it's this area, right? This area here, and remember, this is going to be a curve here, right? It might look straight here, but this is actually a curve. It's actually a curve, right? See that? It's like you take this circle. It's like you take this circle here, right? And you were to, all right, integrate it from here to here, from A to B. From A to B. It's like you take a circle and you were to, you slice up this solid into little pieces. It's the little pieces, and you add up the volume of each of these slices, and you will get the same answer, right? All right, good. So let me give you the version if you have, let's say, all right, something like this, right? And you were to take this and revolve it around the y-axis now, right? How do you find the volume generated, right? So the volume now is going to be V is equal, and this is if you revolve around the y-axis, is going to be equal to, oh, I forgot the A and B here, the A and B here, right? A and B of x square dx, right? Put your pi outside here. So you have to express the curve as x equal to something. I think I made a mistake. This is dy. Down here's dx, down here's dy. Right? So these are the two formulas you will use, depending on whether you are rotating about the x-axis or the y-axis. I'm just introducing this to you. When you do calculus too, you'll see that there are different methods of finding volume that you want to know, where all those methods come from. Good. So let's do some examples. Let's do some examples. Let's say you want to find the volume. You want to find the volume of the solid obtained by, and they do use the word rotating, right? Sometimes about the x-axis, the region on the curve y equal square root of x from 0 to 1, right? To 1. So here's your curve, right? You want to, okay, let me give you an idea what the curve looks like. So the curve, that curve looks like this, right? Looks like that. So we're taking this region here, right? From 0 and down here is 1. Taking this region and we're rotating it about the entire, the x-axis there. When you rotate it, you'll get something like this. You get a solid looking like this. Don't laugh, my right? You'll get a solid looking like that, right? Solid something looking like that. Good. How do we calculate that volume? Well, we're gonna use the formula we just said, right? So V is equal to, as we said, y squared dx from 0 to 1, right? And in this case, y is that. So it's equal to, when you square root x, you get x. And we left out pi from 0 to 1 dx, right? And that turns out to be what? X squared over 2, 1 and 0. So you don't have to, when you put in 0 there, it'll kill the expression, right? Put 1 in there and you get, oh, I left out pi again. You get pi over 2. So that's the volume of that solid that is generated by rotating it at that little area. You get this one? Oh, why do you say nothing? All right, let me take a last one. I'm not getting complicated on you. I'm just doing the simple stuff. So, okay, look at this one. They want you to find the volume of the solid generated by rotating the region bounded by y equal x cubed, y equal 8, and x equals 0 around the y-axis. Notice this, right? You're not doing it around the x-axis, right? So let's try to draw this thing for us. So, okay, this is your core. Y cube, you got to know your y core, your y cube core, right? I think that looks like this, right? So x equals 0 is this line here, the y-axis, right? X equals 0 is the y-axis. Good, so we're talking about that. And where else? Y equal 8. Oh, so y equal 8 is this line here, right? So basically it's this. The curve, y equal 8 and x equals 0. So this is the curve, this is the part, right? So you take this and you rotate it around the y-axis. What will you get? You'll get something like this, right? You'll get something like this. You'll get very much like the curve we just had, the solid we just had, right? It's going to look like that, right? So you get this solid there, right? Good. So we're going to integrate from 0 to 8, right? To 8 there. We're going to integrate from that, right? What are we going to do? We're going to take the integral and put your pi out there of x squared, right? So from this here, or remember x squared dx from 0 to 8, right? So what are we gonna do here? We gotta change. We gotta get from that x equal to cube root of y, right? Or y to the 1/3, right? So x squared gonna be equal to y to the 2/3. So we gotta so our volume is going to be equal to pi integral of y to the 2/3 dy. I think I made a mistake here. This is supposed to be dy from 0 to 8, right? Yeah. So when you integrate this, what are we going to get by? You're going to get 3 over 5 y to the 5 over 3, right? Put 8 here and 0 here. And you put your pi here. So when you finish, you put in, well, put in 0 here doesn't make sense, right? You get 0. Put 8 in there. And I think when you finish, this is what you're supposed to get, 96 pi over 5. That's your volume. Right? Simple as that. I'm not going to get more complicated than this, right? I'm going to stop right there. If you were to do calculus 2 and so on, and advanced calculus, the teachers who are in the class, that is when you get into integration and area and volume and so on. And that is when you're going to understand basically what they're doing here, right? You see this thing here? If you watch this thing, it looks like the area of a circle. So what they're doing, they're taking a disk. They're taking a disk here. And the area of this disk is basically what? X squared pi, right? Pi x squared. Because what? This value here, right? This value here is an x value, right? X. So remember that thing, pi r squared? So this area of this circle is pi x squared. That's what this is. It's like you're taking the disk and you are like, you know, that disk is going to travel from here, from 0 here, from here, right up to there. The volume that it will sweep out by doing that, right? As a matter of fact, it's like, okay, you take a small disk and let that disk grow, and you add up all these thin disks. It will give you the volume of this whole thing, right? They're called Pringles. You watch the thing together, it's all one stack, but it's made up of all these little disks, right? That's what's happening here. And they found out that if you were to integrate x squared with respect to y from 0 to 8, you're going to get the sum of all those disks. I guess most of you might be too young to grasp the concept. But by the time you encounter calculus 2 and advanced calculus, your mind would have matured and you'll be able to think more abstractly as to what's going on there. Good. So we're gonna stop there. And as a matter of fact, that ends the course, right? That ends the course. So let me stop the recording here. Stop recording.